Okay, so just quick announcement before we start the next session. A reminder about the potluck at Brant Robertson's house. So the blue doesn't show up on that projector very well, but underneath today's session, there's the link to a potluck dinner information. So you can go on the conference website, click that link. It has the directions how to get there. Also, it says 6:30 potluck, which is a fine time to arrive. We are going to end a little bit earlier than originally planned. So Brant said it's okay if you want to head over. If you get there a bit before 6:30, that's fine. Also, I don't know whose they are, but there's a pair of glasses up here. So if someone's missing glasses, they're here. So on that, I will pass it over and we can start the next session.
So our first talk will be given by James Bullock. He will be talking about understanding thin and thick disk formation in fire simulations.
Great, thanks so much. I wanted to echo a couple of things people were saying last night and earlier today of what a special conference this is. Definitely want to thank Avishai and Joel and Sandy and everybody. Of course, Andy's been coming as long as I think I've been around to be coming to these things. It's just such a special group. Not only intellectually stimulating with the people here, but the sort of physical environment of Santa Cruz. I think there's something special to remind us that being in these redwoods, I think, always makes me think better, I think. So anyway, thank you so much, Avishai. And I'm going to be returning to a topic that I think I remember working on with Avishai and Joel back in the day, which is trying to understand how these disks form with all this angular momentum and stuff like that. And by the way, Brant and I have been working together about as long as he's been coming here, and this was also something we worked on together. So I want to thank everybody for influencing my thinking, and you'll see how corrupted I've become since I've been working with you with all the bad ideas I'm going to present today. So I want to talk about thin and thick disk formation, in particular with Fire 2 simulations. And as I'll talk about, I think we're actually getting to the point now where with some of these simulations, we're forming disks that are pretty darn thin, and we can actually start talking about how we form thin disks and thick disks, how they're different, and how we sort of begin to understand those different processes. The work I'm going to talk about is primarily going to emphasize work by Anna Yu and Zach Hathan over these three main papers over the last 3 years. There also will be the next talk by Fiona is very much related to this, and she'll talk a lot about sort of understanding the Milky Way in the context of some of these same simulations. And Jonathan Stern is sure to give a masterful talk on Friday with some of the physics associated with some of this hot mode accretion stuff that I'll touch on a little bit today. So the big question is, there's a big question I think people have been asking for quite a long time in the context of CDM is how do you make thin disks in such a model where you've got mergers, everything's so chaotic. Even if you think about cold mode accretion, stuff is crashing in supersonically. How do you make a thin, razor-thin disk in such a model? And more generally, why do the nature of disks seem to change with redshift, and why do the fraction of galaxies that seem to have disks change with mass? These are sort of big, broad questions in galaxy formation. We don't know the answer to them fully, but I think we're sort of beacons we point towards. And of course, JWST is seeing what appear to be more high redshift disk galaxies than were expected based on Hubble observations. We've heard talks about this before. A lot of work here based on this. Brant wrote a nice paper on this. We've heard about it today. So it's, there's this interesting question of, there's more disks at high redshift than we thought. And that understanding is increasing day by day. I would posit and make a bold claim that what do we make of this? Well, we don't know what to make of this because we don't really know how disks form. And so this is a question we have to tackle. So we don't even know what knobs to turn if we want to make more disks at high redshift. So what knobs can we turn in our models to make more disks? Is there an effective efficiency parameter? For example, we're thinking about for making high redshift big galaxies that we can turn up to make more disks. That's a question I'll pose. Now, we've made a lot of progress since the early days in CDM where there were this angular momentum catastrophe. And then, we're here in Santa Cruz. And I think for me, it was really this paper by Piero and his collaborators with the Ares simulation with the banana slug here that I think I remember, sort of in a major way, boy, that looks pretty good. Began to make fairly realistic-looking Milky Ways right around this time. But of course, this work was motivated by a bunch of previous work that comes along. In particular, Jonathan Bird wrote, I think, a fairly impactful simulation paper based on analyzing this work, where he introduced this term inside-out, upside-down galaxy formation. And the idea here is that at early times, the stars tend to form in these sort of tight little bulge-looking things. As time progresses, you begin to form these thick disks, and at late times, you begin to form thin disks. This is very different than the canonical picture where all galaxies start off as thin disks, stuff bangs into them and thickens them. Right? And we heard about that a little bit today. But as we sort of look at more advanced cosmological simulations, these zoom-in high-resolution simulation, this appears fairly ubiquitous. But it looks like modern simulations these days are definitely sort of living more in this inside-out, upside-down picture of disk formation. And we've heard about dissettling. This is consistent with this idea. Flash forward a few years. There was this nice paper by Daniel Servino, Joel Avishai, comparing to Susan's observations on dissettling. And they made this interesting observation that I sort of have noted. Around Z of 1.5, there's a merger. And in that merger, you get this compactification that we've heard Avishai talk about. And only after that point, you start seeing a disk spin up. Then, subsequently, with time, you get this phenomenon that people call dissettling, where it looks like the dispersion's going down, and you move towards something more like a thin disk today. Now, of course, when we talk about dissettling and things getting cool, I think it's important to remind ourselves that the stars themselves are not cooling. You can't take dissipationless stars and cool them. What you're really doing is you're building a thinner and thinner disk over time that begins to dominate the light. The thick disk is still there. You're not really cooling the stars, right? But this is again consistent with this picture, upside down. So what I want to do is kind of extend this chain and begin to look at a set of fire simulations. I'll eventually look at sort of 12 zooms of Milky Way-sized things. These are kind of the coolest looking ones, the thinnest ones. They happen to live in a pair. This comes out of the Elvis on Fire combination, where we have these pairs of systems. We named them after famous duos, and so we have Romeo and Juliet here as a pair like M31 and the Milky Way. And they're both quite thin. Romeo in particular is super thin. In fact, if you look at the circularity distribution of all the stars in this and weight them by R-band light, this is what it looks like. So this is the J component of the specific angular momentum divided by what the angular momentum would need to be on a circular orbit with the same energy. And so a perfectly circular orbit has an epsilon of 1, and you see just like it's almost delta function at 1. This is a very thin disk. So that's striking, right? One of the things I'll talk about in a bit is if we want to classify sort of in a very theory kind of way components, I'm going to name thin disk stars everything with epsilon greater than 0.8. And if I look at only those stars, it does look quite thin, and that's where the spiral arms live. If you look at sort of intermediate epsilons, I'll call that thick disk, and indeed you get like a thicker disk. And then everything, with sort of more elliptical circularities, I'm going to call that spheroid, and you add them all together, you get the disk. Okay, so that's kind of a way to characterize it. And what I want to do is I want to look at how this was built up over time. This is this same galaxy 11 billion years ago. These are all stars that are about 100 million years old 11 billion years ago. This is the circularity distribution of those stars. If you look at the plot, it looks like a mess. But the circularity distribution is peaked towards 0. It's very isotropic. This is 8 billion years ago. Suddenly now we see a clumpy disk. You see that epsilon distribution looking a little bit more like a thick disk epsilon. And then I go 5 billion years ago, and now we're moving in towards that thin disk regime. Right? Now I'm going to look in every snapshot, just those stars, I'm going to look where they end up today. These stars look like a spheroid today. These stars look like a smooth thick disk today. These stay pretty thin. Right? So this, in the paper this came out, this is Yu et al., we called this born this way. Because all the stars that are in the spheroid today were kind of born with similar orbits. So there's not that much heating going on. There's some heating. We talked about that, right? I mean, this is a little thicker than this. So there is a little bit of heating. We heard about that, some evidence of that today in the real universe. But I would say to first order, you're sort of born with a spheroidal orbit, you end up with spheroidal orbits. You're born with thin disk orbits, you stay pretty thin. I mean, there is some heating, but what we're seeing is it's not that much change. So the thing I'll talk about now, and we'll hear, I think Fiona will talk about this next too, is that we basically see 3 phases of disk formation in these simulations that end up Milky Way size. There's this early phase where things are bursty and chaotic, and then there's a spin-up phase where the circularities start to approach something more spinny. And then there's this late time phase where it's quite thin. There's 2 colored lines. The shaded, the red line is what the stars, the circularities of the stars at birth. Right? So it's kind of moving around, there's starbursts and stuff. But you know, it's pretty spheroidal, it spins up, and then it gets very, very circular at late times in terms of the birth ages. And the gray is what it looks like now. So things kind of smooth out. But if you remind ourselves of what we're going to call thin, thick, and spheroid, there's sort of this spheroidal formation phase, there's the thick disk formation phase, and then there's the thin disk formation phase. And Fiona will call these, or in her paper, she calls these pre-disk, early disk, and late disk. But, you know, same deal. There are these kind of 3 phases. So what I want to understand is, why do we have these 3 different phases? And the first thing I want to talk about is the one I'm more confident about, which is the late time transition from thick to thin. And what I'm going to suggest is that this has to do with the virialization of the inner CGM. So if you look at the inner CGM in these fire galaxies, you see that there really is a transition. At early times, it's very clumpy and chaotic. This is when the cooling time is less than the free fall time, so you have all this cold stuff slamming in supersonically into the system. But then as time progresses, when the cooling time over the free fall time becomes longer over time, as the halo gets more massive, basically, you cross this characteristic scale, the inner CGM virializes, and suddenly now the way gas is getting into the disk is it's gentle and coherent and it's subsonic. That's a much more gentle process. And in fact, we see that if you plot the circularity of the orbits over time, for here's Romeo and here's Juliet, and here you plot this parameter, which is basically, if it's bigger than about 2, the inner CGM is virialized. When the inner CGM becomes virialized, suddenly the orbits become very circular, razor thin, of young stars. So we're connecting what the CGM is doing to what the morphology of the stars are as they're forming. This thing virializes early, has an older thin disk. This thing virializes late, has a younger thin disk. What's happening physically here, let me just skip forward. What happens physically here is if you now look at the angular momentum distribution of the gas as it's flowing in time, if you back up about 500 million years before it enters the disk, the angular momentum distribution of the gas is actually pretty broad. Some of it's spinning one way, some of it's spinning the other. And then it narrows and mixes and becomes extremely coherent and co-rotating prior to entering the disk. The temperature stays hot and it cools actually right when it enters the disk. What happens is it compresses. Because it compresses, it heats up a little bit more. So it sinks a little bit more and compresses and heats up a little bit more and stays hot all the way in until angular momentum support stops it. It no longer can fall in, so it just cools. So it cools out right on the edge of the disk, right as the angular momentum gets concentrated, and you build this very thin disk. Here's an example of a galaxy that does not end up with a thin disk. The gas comes in very incoherent, it never mixes. It comes in cold mode and never mixes. So this is a cold flow system, very turbulent. The other one I showed was a hot mode. It came in very smooth. So these two halos actually have very similar spin parameters, right? So this is sort of obvious, but halos of all masses have the same spin parameters. So it's not just the spin parameter, right? There's something much more complicated going on. You have to mix that angular momentum, make it coherent to land in a thin disk. And this is enabled if you have a hot halo, specifically a subsonic flow. You can get these thin disks. Here's 12 Milky Way mass halos from the fire group, and the thin disk fraction actually correlates with the time of the inner CGM virialization. So there's systems that have basically CGM virializes very late. You really don't make much of a thin disk, and Romeo is the one I've been focusing on that virializes the earliest. The median age of thick disk stars correlates with this time too, right? So you would have like an older thick disk and an older thin disk in models the CGM virializes earlier, right? So for the Milky Way, if we say our thick disk age is about 9 billion years, this would suggest the CGM virialized around 6.5 billion years ago, for example, which we would sort of say is at the edge. It's about the thinnest we see. So that's what I think is going on between phase 2 and phase 3. I think it's when the inner CGM virializes. The second piece I think is a little less clear, but I'll tell you where my head is right now, but I'd like to chat about it. There's this very early phase where things are very chaotic. The orbits are very, very radial of new stars, and those stars end up as spheroids today. And then there's this spin-up phase, where you begin to make these kind of thick, clumpy disks. Phil Hopkins had a very interesting paper where he ran just a bunch of models and was sort of trying to turn knobs and figure out, what do you have to do to make more disks? And one of the things that he noticed is that if you have very centrally concentrated potentials, it basically gives a center, so you kind of know how to measure the angular momentum around something, and that begins to enable the formation of disks. And there's other things too. It stabilizes the disk to certain instability modes, etc. But this is kind of the picture. One thing that's kind of interesting is here's an example of a system where you dial up the central potential, and this is the circular velocity curve. And when the central potential is not peaked, you end up forming stars in this this is just gas, but the gas tends to be very sort of have circularities around 0. And then when the rotation curve starts to peak and you have something to orbit around, that's when this kind of thick disk transition begins to turn on. And so it might be a transition where as soon as the potential becomes centrally peaked, you have something to orbit around. That enables it. And this is just an example of a bunch of different simulations. This is the circular velocity curve. It's the radius divided by the radius of the galaxy. So when it sort of peaks in a regime where like the stars and gas can orbit around something that looks kind of like a Keplerian potential, you start to see a little bit more of that thick disk spin up start to happen. So that could be what's going on there. We're trying to investigate this a little bit more carefully over time. But this is, it's an interesting idea to think about what drives that initial step. So, there's a model here where you have this initial phase 1 where things are very chaotic. At some point, the central potential, maybe it's a compactification event, maybe it's a merger that drives stuff to the middle. You suddenly have something to orbit around, and then you have this kind of clumpy, thick disk phase. And then at some point later, you have this inner CGM virialization, and then the thin disk, and then it'll really build out of that gas as it's landing quietly in the disk. So that's the toy model I'm going to present. Let me just say, so I'll close with this in case people have questions. I've got a bunch of backup slides, but I'd rather finish a little bit early. So this is what we're finding. There's these 3 phases. And again, none of these quench. I'm not getting into galaxies that quench. These are all they end up being sort of Milky Way type systems. In the early phase 1, you have this chaotic morphology. The star formation, by the way, is very bursty during this period. And the orbits of young stars are quite radial. If you look at where those stars end up today, they're in sort of a spheroid. Phase 2, there's this clumpy, puffy disk phase where things are pretty chaotic. And if you track where these things end up today, they have very thick disk orbits today. And then finally, there's this thin regular disk phase where now The star formation is no longer bursty. The gas is landing quietly from this hot mode accretion, and most of those stars remain thin. Of course, if there's mergers and other things can perturb those stars and thicken it, but we find that that's actually a secondary thing to sort of how the orbits were when they were born. I think this thick disk spin-up phase perhaps can be enabled by essentially concentrated potential. And the second phase, the cool down, the very thin disk phase, this is enabled by this hot mode accretion that allows the gas to mix and become very coherent in taking momentum before landing in the disk. It's all orbiting in the same direction. Okay, that's it. Thank you. Lots of questions.
So, James, as you saw from Viraj Panju's talk, and as you probably know from the Vandervelde 2014 paper and Hawen Zhang, Premack et al. 2019, there's strong evidence based on axis ratio distributions that galaxies that are less than about 10 to the 10 solar masses, or 10 to the 9.5 anyway, even out to high redshift now, are prolate. Where does that fit into your picture?
I mean, it's a great question. I don't know. I mean, one thing I would say is it is interesting to me, as I look at, I haven't thought about the shapes at all, but, if I look at these, in this phase, they look kind of like, there's sort of this surfboard regime, right? Where maybe that's what's going on. It's not necessarily prolate. It could just be these surfboards. I don't know. I don't know how you see, certainly if you have a prolate system, it's not going to turn into a thick disk, right? So, I'm really talking about, my talk right now is about how do you make Milky Ways over time.
But very likely the Milky Way started out, most galaxies seem to, these prolate gas. Then there's typically a compaction event, makes that center. And the compaction event occurs around the time when the center becomes dominated by stars rather than dark matter. That happens because there's been this big flow of gas into the center. After that, I think the story is pretty much the way you described. But there is this early stage, and I've wondered whether the fire simulation...
I haven't looked. Maybe.
Okay.
I haven't.
I've asked Phil
maybe it's here.
A lot of times, and I never...
Yeah.
But
we should look.
If they look like the real universe, they should start out prolate.
We have lots. Okay.
I think the prolate phase relates more to the low mass chaotic phase than to the right, and it's a stellar prolate. Once you have a central compaction, you get these disks, and I think it's generic. We see it in our simulations as well.
Okay. Sandy up in the front too, by the way.
When you showed the evolution of the gas fraction of disks as a function of redshift, have you looked if it's not actually a function of mass? Because the hot mode is usually above 10 to the 12 halo mass, quite robustly all redshifts.
Yeah, I don't think with the current setup that we can explain that evolution with hot mode, because it just happens too late. We just don't get enough disks. So I think if we demanded all disks at high redshift to be hot mode, I think we'd be in trouble. You can play around with trying to get subsonic flow with other ways, cosmic ray pressure, perhaps changing the metallicity to move those things around a little bit. But I really think that these higher redshift disks probably it's more these things. But it's a good question, and we need more statistics to think about it. Brant's had his hand up. Sandy's got her hand up. Can we go Brant and then Sandy?
But we really need to move on. We thank Jim again, and we continue discussion in break.
Oh.
So our next talk will be by Fan, and